Linear functions. Our objective is to describe the graphs of linear functions. So a linear function is a relation. So remember from our last section, we talked about a relation. Is a relation that can be written in the form f of x equals mx plus b, where x here, again, see there's my x there, that is your input. So here we're just using function notation. So it's my input, which means it's my independent variable. Independent variable. Okay. And m and b are just numbers, are numbers. Okay. So your m and your b are numbers. Okay. So this is some new information. We haven't really seen this guy before. F of x equals mx plus b. We can rewrite this because we know f of x is the same as y. So let's write it as y equals mx plus b. Okay. And then we can rewrite it. I'm going to subtract my mx from both sides. So on my left side, I'm going to have negative mx plus my y. On my left side, these add to 0, and I'm just going to have a b. Okay. Now, if we look at this, does this fit the definition of the standard form of a linear equation? If we go back to chapter 3, there's our 3-1 notes. If you notice, our standard form of a linear equation here was ax plus by equals c. So let's go ahead and let's write that down. So the standard form for my linear equation was ax plus by equals c. Now, if I look at this, this looks a lot like that, in that my m is my a. So basically I have ax. My b is 1 by. And then my uppercase c in this case is actually a b. So it fits that same pattern. So basically a linear function is me taking a linear equation and writing it in function form. Okay. So a linear function, okay, is just a linear equation, which we did in chapter 3, written in function form. Okay. What we mean by function form is with that whole f of x notation. So basically, we solved this linear equation. We solved this guy right here for y, and then replaced it with an f of x. So all of the things that we know about linear equations, we can now apply to linear functions. So describe the graph of a linear function. How do you know? Well, it's a line. Because why? It's a linear equation. And all linear equations graph lines. Okay. But what if your m is 0? So let's go ahead and let's look at my function. F of x equals, again, it's mx plus b. What if this guy right there is 0? So we'd have f of x equals 0 times x plus b. Well, what's 0 times x? 0. What's 0 plus b? Just b. So I'm going to have an equation, just f of x equals b. Okay. So in other words, I don't have an m. Okay. So what if my m was 0, my b is 4? So what is the corresponding y value for any x value? Okay, what does that mean? Let's just go ahead and let's plug in. Y equals f of x, m is 0, 0 times x, plus my b is 4. So I just replaced my m with a 0, my m with a 0, and my b with a 4. Well, from the last bit that we did, we know this is 0 plus 4. So I'm left with f of x equals 4. We actually did a problem very similar to this on our last practice. What is the corresponding y value for any x value? Meaning, when I put any x value in, I don't know, x value of 1, what do I get out? Well, I don't have any place to put an x over here. There's no x. So my output is 4. When I put in a 20, my output is 4. When I put in a negative 100, my output is 4. Because what this function tells me is the output is always 4. Okay. The output is always 4. So what is the corresponding y value for any x value? 4. 4 is always my y value. Doesn't matter what my x is. If my x is 1, if my x is 20, if my x is negative 100. So describe the graph of the function you wrote. Okay, well, to help me get a visual, I'm just going to graph it. Not going to be a perfect graph. It doesn't say to graph it. It says to describe the graph. I'm going to draw the graph to help me out. So if I look at these points up here, when I put in an x coordinate of 1, my y coordinate is 4. So that would be the ordered pair 1, 4. The next one, an x coordinate of 20, y coordinate of 4. Negative 100, 4. If I graph these points, over 1, up 4, over, I don't know, way over 20 over here. I don't know, I'm going to go over so far, up 4. Negative, I don't know, way over here, up 4. If I connect my dots here, what kind of line do I get? I get a horizontal line. The line is horizontal. Since y always equals 4. And because it's very similar, if we again think of this function notation, f of x equals 4 is the same as y equals 4. And from our previous chapter, we know that that's going to be a horizontal line, y equals 4. All right. So write the linear function whose graph is shown. So if we look at this guy, he's horizontal. Okay, I can go ahead and put some ordered pairs on there. Here I've got the point 1, 3, 3, 3. What do we notice about all these points? The y coordinate is always 3, so my y coordinate is always equal to 3, but I want it to be a linear function. I need to write this in function notation. So I'm going to use g of x equals 3, function notation. So if it's asked for a function, you want to write it as a function using that f, g, h, whatever name you want to give it. Okay. All right, so let's go ahead and let's graph some linear functions. So we're going to go ahead and we're going to graph some over here. Okay, so first I'm going to graph this guy. F of x equals 3x minus 2. So I'm going to go ahead and start with my axes. And now I'm going to get some ordered pairs for this guy. So I'm going to come over here and I'm going to create an x, f of x table. My favorite number to put in is always 0. So I need to figure out what is f of 0. I'm going to do that over to the side, f of 0. So I'm putting a 0 in for my x. 3 times 0 minus 2. 3 times 0 is 0, so I get negative 2. So it's going to have the point 0, negative 2. Okay, so now what about we put in a 1? F of 1. 3 times 1 minus 2. That gives me 3 minus 2, which is 1. So I have the point 1, 1. Okay. F of, I don't know, 2. 3 times 2 minus 2. 3 times 2 is 6, minus 2 is 4. So I have the point 2, 4. Okay. Those look pretty good. They're all in a nice line. So I'm going to go ahead and do my best to connect the dots. Again, it's hard using ruler on my iPad, but I'm going to do the best I can. Let's see. There we go. Pretty close. Okay. So there is my graph. So again, we just plotted points. All right, let's go ahead. Let's try this next one. All right, I'm going to put my axes in. Okay. All right, so let's go ahead and let's get some points for this too. X, g of x. So instead of y, x, g of x. And again, I'm going to plug in a 0. 0 is one of my favorites. So I need to find g of 0. So it'd be 1/2 times 0 plus 1. 1/2 times 0 is 0 plus 1 is 1. So I have the point 0, 1. Okay. All right, so what about 1? G of 1. All right, I don't know about you. 1/2 times 1 plus 1. 1/2 times 1 is 1/2. 1 1/2. I don't want to graph that, so let's skip it. If it's not a nice number, just skip it and get some more, because really I just need so many points, right? So let's find g of 2. 1/2 times 2 plus 1. 1/2 of 2 is 1 plus 1 is 2. So I have 0.22. 2, 2. Okay. So it looks like odd numbers aren't working well, so we'll go ahead and do 4 next. G of 4. 1/2 times 4 plus 1. So 1/2 of 4 is 2 plus 1 is 3. 1, 2, 3, 4 of 1, 2, 3. All right, those look like they're in a line. Again, you always want to graph more than just 2 points. And look at how I extend my graph all the way through. Like I extend this all the way through, and I probably should have went farther this way. Go all the way through. Don't just connect the dots just from here to here. Okay, draw that whole line. Put your ruler on there, use a ruler, and have it go all the way through. So there's my graph of g of x. All right, last one. Let's go ahead and let's graph h of x. Let's get my axes up here. All right, so I'm going to create an h of x table now. Again, I always love to do 0 first. Negative 3/4 times 0 minus 4. Oh, sorry, this is h of 0. Negative 3/4 times 0 is 0 minus 4, negative 4. So I have the point 0 down 1, 2, 3, 4. Okay, now I have to take whatever number times 3/4. So I'm thinking 1, 2, or 3 isn't going to work well just because this has got a denominator of 4. So the next number I'm going to try is 4. Negative 3/4 times 4 minus 4. Negative 3/4 times 4, negative 12/4, which is negative 3 minus 3, negative 7. Negative 4, 1, 2, 3, 4, down 1. Oh, positive 4. 1, 2, 3, 4, down 1. 6, 7 puts me there. All right, so I'm thinking I'm going to get way bigger, so I'm going to go negative 4. Sorry, this was h of 4 notation. H of negative 4. Negative 3/4 times negative 4 minus 4. Negative 3/4 times negative 4. Negative 3 times negative 4 is 12. Divided by 4 is 3. 3 minus 4 is negative 1. So negative 4, negative 1. Oh, yay, they're all in a line, so I can go ahead and connect the dots. Okay. All right, so it says, what do we notice about M and B? Okay, I don't know if you noticed it. You might not have, but let's look at all the B's. My B in this case is negative 2. My B is negative 2. In this case, my B is 1. And in this case, my B is negative 4. Looking at each of these, where does a negative 2 show up when I'm graphing it? Right there. Where does the 1 show up? Right there. Where does the negative 4 show up? Right there. And if you notice on your graph, there's my negative 4 right there. There's my 1. And on this first one, there's my negative 2. So what do we notice about that B? B is the y-intercept. How awesome is that? Which makes sense because from what we noticed up here, when m is 0, or when this first part is 0, when x is 0, in this case, when x was 0, this part ended up being 0, so you're just left with that. And we know at the y-intercept is the ordered pair 0, b, because my x is 0. So when x was 0, x was 0, x was 0, and all of them. Okay, now we need to figure out where that m showed up. The m is a little harder to find sometimes. Here, let's go ahead and identify what the m was in all of these cases. I'm doing it in green here. My m is 3 in this case. Here, my m is 1/2. And on this one, my m is negative 3/4. Okay. So it might be a little harder to see. But if you notice, if I was to find the slope here, this goes up 1, 2, 3 over 1. So rise of 3, run of 1, up 1, 2, 3 over 1. The slope of this line is 3. And remember when we talked about slope, we said we use m for slope? Yeah, we still use m for slope. M is the slope. So we can actually use that to graph. If it is written in a linear function form, f of x equals mx plus b, or if it's written as f of x equals mx plus b, or even y equals mx plus b, I can graph it using the slope and the y-intercept. Hence, we tend to call this slope-intercept form. Slope-intercept form is f of x equals mx plus b, or y equals mx plus b, is called slope-intercept form because we can look at it and find the slope and the y-intercept. So we can graph these old school. So if I go ahead and graph like this one, we're going to graph this one two different ways. We can graph it our old way, create our table, my x, f of x table. Plug values in. When I plug in a 0, so I need to find what f of 0 is. 3/4 times 0 plus 2. 3/4 times 0 is 0 plus 2 is 2. So I have the point 0 up 2. I'm not going to put in a 1 because, again, it's 3/4. So let's go ahead and put in a 4. 12/4 is 3 plus 2 is 5. So I put in a 4, got out a 5. 1, 2, 3, 4, 1, 2, 3, 4, 5. And then I'm going to put in a negative 4. F of negative 4, 3/4 times negative 4. Negative 12 divided by 4, negative 3 plus 2, negative 3 plus 2, negative 1. Negative 1, 2, 3, 4, negative 1. And I get this nice line. Again, you always want to make sure you graph more than 1 or 2 points. Okay, so that's one way I can graph it, the way we've been graphing. Or I can graph it using the slope and the y-intercept. I come and look at this graph, identify the slope and the y-intercept. My y-intercept is 2. My slope is 3/4, which tells me rise is 3, run is 4. So you actually start here. You start at my y-intercept. So I know this needs to cross the y-axis at 2. So there's my y-intercept right there. So I mark my y-intercept right there. My y-intercept, and then my slope. So from this point, I go rise of 1, 2, 3, run of 1, 2, 3, 4, puts my new point there. So rise of 1, 2, 3, run of 1, 2, 3, 4, puts me there. And I can keep going. Rise of 1, 2, 3, run of 1, 2, 3, 4, puts me there. Rise of 1, 2, 3, 1, 2, 3, 4. And I get this nice line. Connect the dots. Now, if you notice, it's the same as this line I got over here. We have the point -4. 1, 2, 3, 4, -1. Sure do, right there. Okay, so it is the same line, except I didn't have to find all of these points. I was just able to identify slope and y-intercept. Okay, so let's do a bit of matching. We want to match each equation. So the first thing is you can either doing it by plotting points or using slope and y-intercept. Slope and y-intercept tends to be faster. So I'm going to look here, and this first one, it needs to have a y-intercept of -2 and a slope of -3/4. The -3/4, so I know my line has to be going down. So right away, going down. Oh, that eliminates that one. It can't be that one. So this first one's either going to be A or B, but it needs a y-intercept of -2. It needs to cross this y-axis at -2. This one crosses the y-axis at 2. Nope, this one crosses the y-axis at -2. And then if we do slope, the slope needs to be down 3, down 1, 2, 3, over 1, 2, 3, 4. Yep, hits it. So number 1 there is B. Okay, so we used up B. Number 2, a y-intercept of 2 and a slope of -3/4. Again, still needs to be going down, which is going to eliminate this guy. So this is the only one that's going down yet. It does have a y-intercept of 2, which we wanted. And it goes down 1, 2, 3 over 1, 2, 3, 4. Yep. So this one has to be, this one has to be A. And this last one, a y-intercept of -2, which this one has, and then a slope of 3/4 up 1, 2, 3 over 1, 2, 3, 4. Yep. So that one has to be C. Okay. So now we have to talk about one last thing before we get into an application type problem, and that's the difference between a continuous function and a discrete function. Okay. A continuous function is one that has no gaps or breaks, meaning I can draw it, can be drawn without lifting the pencil. Okay. All of these up here, all of these are continuous. And most of the ones we've done so far have been continuous. We have had a couple in the past that have been discrete. What we mean by discrete is it's made up of unconnected points. Okay. I always like to say it doesn't include the in-betweens. What I mean by the in-between numbers, the numbers in between 1 and 2, or the numbers in between 2 and 3. So this one, so a continuous function is going to look more like this. A discrete function is going to look more like this. We don't include the in-betweens. Many things in real life, this models more real life, models real life examples. In many situations in real life, in-between numbers don't make sense. You can't go in and buy 1.5 shirts. Okay. I'm not going to buy half a sandwich. I'm not going to make half a pie to feed everybody. Okay. So the in-betweens don't make sense in real life situations. Okay. So let's go ahead and we're going to look at a real life type problem that models a discrete function. So Cameron received a bubble tea gift card for his birthday. Write a linear function for the amount A in dollars left, so the amount left on his gift card after X bubble teas are purchased. Then graph the function. Okay, what does the value A of 20 represent in this situation? Okay, first thing I'm going to do is try to make sense of this problem by creating a table. He got an $80 gift card. So over here, if you notice, you got an $80 gift card. Bubble teas cost $4. Okay, so I want to create a function, and they said to have the function be A of 20. Okay, so we know my function needs to be, write a linear function for the amount A in dollars left on the gift card X. So X is dollars. X is number of bubble teas. And A of X equals the money left on card. Okay, so I'm going to create a table to kind of make sense here. Okay, so we start out with, if I don't buy any bubble teas, if I buy none of them, I will have $80 left. I didn't buy any. Okay, if I buy one, well, that would be 80 minus one bubble tea, which is $4. So that would be 76 bucks. If I buy two, 80 minus two bubble teas, 4 times 2. So 80 minus 8 would be 72. Okay, if I bought 10 bubble teas, 80 minus 4 times 10, 40 would be 40, so forth and so on. So it looks like if by writing out my steps here, instead of just writing the number, writing out my steps, it looks like, and this first one will be 80 minus 4 times 0, that my function, A of X, is my $80 minus 4 times X, where X again is the number of bubble teas. Okay. Now, this doesn't really look like a linear function because it's supposed to be, again, my linear function notation, f of x equals mx plus b. My x is here. So I'm going to go ahead and I'm going to rewrite this. This is plus and negative. So I'm going to write it as negative 4x plus 80. Okay, which tells me I'll have a y-intercept of, my y-intercept is 80. My slope is -4, which makes sense. I go down $4 every bubble tea I buy. And if I don't buy any, my y-intercept would be 40. Now, negative numbers do not make sense in this situation. I'm not going to go in the whole money. I'm also not going to buy negative bubble teas. So negative numbers don't make sense. So I'm going to have the point 0, 80. I don't know. What do we want to count by? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. Count by fives. So there's 80. It's my intercept. Okay. All right. And so then 2, okay, the only bummer is going by fives is my numbers aren't even. That's odd. That's all right. We're fine. So I know after 10, so this here, we're counting by fives here, so we better mark it. 5, 10, 15. And then this up here is 80. So there's one of my points. And then I need to go down 4 each time. So this will be 1, 2. So I need to go down 4 over 1, which is going to put me here. Okay. So 2, we had 72. Put me here. Down 4 over 1, down 4 over 1, down 4. Okay. Down 4 over 1. So at 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know at 10 I should be at 40. 5, 10, 15, 20, 25, 30, 35, 40. Again, down 4 over 1, down 4. We'll keep going. Okay, kind of like that. I kind of got off a little bit. Counting by 4s is tough when we're going by 5s. Okay, this one should have been a little, we can fix it a little bit. Let's fix some of these in the in-between. Okay, I'm going to go up 4 over 1, up 4 over 1, up 4 over 1, up 4 over 1, 4 over 1, up 4 over 1. There we go. Better. Okay. All right. So if we go ahead, and if you notice, I didn't connect my dots. This is a discrete function. You can't buy half a bubble tea. So by connecting the dots, if I was to connect the dots here, that would tell me that I could put in a number in between 0 and 1. I could put in a half. I could put in a third. I can put in 2/3. Okay, if I was to connect the dots. But we can't. We can only put in those whole numbers. So this is a discrete function. So it's going to be a bunch of not connected dots. Okay. All right, so we go ahead and we keep going. Okay. So dot dot dot. Okay. We can keep going. It's going to keep going down, right? Now we get down here. Now it says, what does the value a of 20? So it says try my linear function. We did. We've got it right here. What does a of 20 represent? I don't know. Let's put a 20 in. A of 20. A of 20 equals -4x. Oh, 20. -4 times 20 plus 80, which is -80 plus 80, which is 0. What does a of 20 represent? When his gift card, so a of 20 equals 0. That's when he can buy up to 20 bubble teas before running out of money. Okay, so it tells us our 0 point. Okay, right, so again, it makes sense in this case when graphing it to only graph positive x's and positive y's, which, if you remember, that is quadrant 1 in our graph. We use Roman numerals, quadrant 1, because negative bubble teas and negative money don't make sense. I want to talk a little bit here about domain and range. What is the domain and range of this function? Okay, might be easy to say the domain. Again, the domain is our x's. What numbers can I put in? If you notice, I put in numbers from 0 up to 20. So it might be easy for us to say the numbers in between 0 and 20. Okay, but be careful. I can't, because I can't include the in-betweens. So my domain is just the whole numbers, 0, 1, 2, 3, and then I would go dot, dot, dot up to 20 and close it up. So if I was to do it all in one line, I would go 0, 1, 2, 3, dot, dot, dot. Keep going like that until you get to 20. Just the whole numbers from 0 to 20. And my range is the multiples of 4 from 80 on down. So 80 minus 4, 76, minus 4, 72, dot, 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 until I get to 0. Okay, because I can't include those in between. The value of my gift card is never going to hit 50 bucks because I can't get there by going down by 4s each time. Okay. All right, so this is what a discrete function looks like. Again, you don't connect the dots if you can't include the in-betweens.